So I'm going to talk about the work I do at Los Alamos in DevOps for the various code teams that I work on. A lot of code teams at Los Alamos have adopted Spack as their primary way of managing their dependencies. Similar to how CMake has become the de facto standard for build systems for C++, Spack has become for us mostly the de facto standard of installing HPC software. And so, but when you look at how the code teams have adopted Spack, initially everybody was doing their own thing. And so a lot of my work was trying to bring them together and follow one uniform way. Okay, so this talk has three parts. First, I'll talk a little bit about what are the general problems I'm trying to solve. Then I'll show you how I use just regular Spack to drive my CMake-based workflows. And then finally, we'll talk about the Spack deployments and how they're structured. Okay, so what are we doing? We're building C, C++, and Fortran HPC codes that have to run on our trial app systems. So that's Los Alamos, Livermore, and Sandia. And so they have to run on CPU-only systems or some GPU-accelerated systems. And it's a mixture of research codes and production codes. So while we're developing these codes, we have a whole range of different configurations we have to care about. We do release builds, debug builds, everything in between, all kinds of configurations of our own code with features turned on and off, all sorts of compilers we care about, various acceleration modes turned on and off. And then we have various communication stacks we have to support. So all sorts of MPIs, maybe a little bit of GasNet. And of course, then you have the differences in the hardware itself. So various generations of the GPUs and maybe different interconnects you have to care about. Okay, so it quickly explodes. And we as the code teams, we have to test on all of these different configurations. And so we manage this complexity through automation. We use GitLab for our source code management, and we use Giacomo CI runners to directly launch jobs directly on our trial app systems. And so not typically the big systems. We have sibling systems that are identical in their hardware and their software stack. And so typically the way you set this up, you have merge requests pipelines that do some testing. If you have more elaborate tests, you run them on the main branch. And the really expensive ones that take for a long time, you might use scheduled pipelines that are nightly and weekly. So what you see here is a typical pipeline for a research code. And what we're trying to optimize here is really the developer story. So what happens when things fail? So the number one complaint you have here from developers is, how do I recreate this CI job? So what are the steps? And so after a lot of work and different iterations, the answer I have for a whole range of projects now at Los Alamos, every single green dots here and the red dots, every single CI job has at the very beginning of its CI log something like this. So a short description of what you have to do to get exactly the same kind of CI run on that particular cluster. So it's the same on all clusters. It's the same on all for all codes. So once you learned this system, you have all the developers know this workflow now. And so it's basically go on the cluster, somehow get the code, and then depending on the system, here's the scheduler line that you have to do to get the same partition at the same type of compute node. And then there is this magic script at the very bottom that does all the Spack-specific stuff. And so hopefully by the end of this talk, that magic line isn't very magic anymore. Okay, so to talk about this, I have to first show you how I use Spack to drive our CMake-based workflows. I assume that the developers all understand a CMake-based workflow, so you have the source code with the CMake configuration files. Together with the build environment and the build configuration, CMake generates our build system for us. With that, we can then build and test, even install the code, and maybe submit our test results up to C-. Now, the difficult part about this is that the build environment and build configuration. The build environment is all the things you need to build, link, and run your code. And the build configuration is what you inject into CMake to create a compatible build system for that environment. So when people start learning about Spack, they eventually discover Spack environments. They see it as a pip replacement or a package manager. They define their environments with all their dependencies, and they let Spack install them, and out of Spack comes a concrete environment which you can then use as a build environment. And this is where a lot of code teams then just stop. They have their existing workflows, their ginormous scripts that were using module files and have some extended logic of recreating a compatible build configuration for that build environment they just generated. And so I'm here to tell you, well, what I tell these teams, we have a tool for this and it's called Spack. It can just generate the build configuration for you. And the only thing you have to do for this is you have to write your own Spack package for your own code. Now for this audience, this shouldn't be a big of a surprise. From a high level, a Spack package just tells you where do you get the source code, which version exists, what configuration options exist, and depending on all of this, what dependencies do I need for the code. And all of this then gets distilled into the build option for your build system, in this case CMake. So once you have your own Spack package, you already have that logic encoded in a Python code. You don't have to recreate the whole thing in shell script or GitLab YAML files again. Just make use of that logic. You have now Spack environments for your own code where you can create constraints for yourself or your dependencies. But you should not see Spack environments as an encoding for your environment. It is also an encoding of your configuration for yourself. Now, you solve the deployment problem once you have a Spack package. You can go to your users and say, here's a Spack environment, and you can install our software and use it on, let's say, El Capitan. But this is not what we want usually for CI/CD. We want to stop earlier and have iterations in the build process. Like we want to make changes to source code, rebuild, test again, maybe change a little bit in our concretization to test something new, maybe a new version of Cocos, and so on. So what we actually want is to interrupt this process. And I'm going to show quickly how this is done with regular Spack. So you activate the particular configuration you're interested in. You tell Spack, I already have a source code checkout in my CI. So take that one, and I want to have a build folder over here. You don't have to clone anymore, and this checkout, please consider it as the main branch of my project. So follow the same concretization rules for this. Now that I have to concretize again, I install all the dependencies that are necessary to build and generate this concrete environment. And then the final step is making use of our Spack package. We generate the build system folder using Spack install, and we interrupt it after the CMake step. In order to use now this build system folder, we have to also use the Spack build environment. So that's all the environment variables that set the necessary environment settings for the build wrappers, the compiler wrappers, and all the other things that maybe have been changed by your dependencies in your environment. There's two ways to do this: interactively with the build env command that drops you directly into the subshell, or what is more scriptable is by dumping it into a sourceable script file. Okay, so once you have that sourceable script file, you can then run CMake directly in this environment. The first thing I do is typically turn off this verbose build, which Spack has on by default, which is really just noise for most developers. But you can run any other CMake command now once you have sourced that environment. So now what you can then do is write little shell wrappers around these commands. So here you just see that I wrap this whole thing into a subshell, and so I don't pollute my my outside environment, and I wrap this into a function that I can reuse. Similar, all those commands you saw earlier about activating the environment, telling Spack where the source code is, where my build folder is, installing your dependencies, and generating the CMake build folder and the Spack build environment, all of those are wrapped into shell functions. And so the magic script really is nothing more than a bunch of shell functions executed in a predefined sequence. And so the benefit of doing this is that you source it at the beginning, you have all the shell functions already in your context, and you can always do Control-C, interrupt the sequence, and then make modifications in your environment, and then continue on using those functions. So nobody wants to, all the commands I've been showing, usually doesn't want to understand those commands. And so this lowers the barrier for using this. If you just want exactly the same environment as the CI, this brings you to the same end, so the same build folder, same configuration, but then you can make modifications, and as you dive in, you might have to learn more Spack commands, reconcretize, and so on. Okay, so what we haven't talked about so far is these first two steps, how to make that efficient for CI. So that's getting Spack and the environments. So this is where we now jump into Spack deployments. For me, a Spack deployment is not just a particular checkout of Spack, but also the configuration for your particular site, your cluster, and maybe particular settings for your project. I have a CI pipeline that creates these deployments for every single cluster that we care about, and it builds out the environments for all the different configurations that we have for one or how many codes you support. And so the way these configuration files are structured, here you can see on the left simplified folder structure, and on the right the basic structure of such a Spack environment. So I use per system folders that each contain folders for the environments, and then there's a shared configuration per system and a shared configuration per code. Okay, so a Spack environment consists of a project-specific list of configurations and system-specific configurations. So a project-specific one would be, for example, which package versions of your dependencies do you want? Or what additional Spack repositories do you need? The system-specific configuration would be which compilers does the system provide, or which Cray MPitch is installed, or which Rockham version is installed. And then all of these are further specialized using the environment-specific configuration. I have two more notes about this. Here you see that I've used this $Spack relative, so it's actually an absolute path relative to the Spack installation. The reason I do this is because this way I can have arbitrary complex folder structures to organize my environments. So I can have multiple codes sharing this deployment. I can have groupings of environments, maybe all of the OpenMP and all the CUDA environments are grouped together. And the second thing I wanted to point out, the requires here is using the list syntax. If you have other requirements, you specify in the project-specific settings and in the system-specific settings. As long as it's a list, the final concretization merges those lists, so you can be more and more specific as you merge these. Okay, so as I said, I have a CI pipeline that generates these deployments, but they are shared, but they are not writable by users or developers. Instead, what we do is we replicate these Spack deployments for each CI job or for a user, and they are connected back to the original Spack deployment as using it as an upstream. In addition, I'm also providing a bootstrap mirror and a Spack mirror in the original deployment. So this has benefits for offline usage. So typically, compute nodes don't have network access. So if a developer is on a compute node and needs to recompile something or additional things, it can make use of that mirror. Yes, here's just an explanation of how that Spack environment then changes. So you just have additional includes, which points to the bootstrap mirror, the upstreams, and the source mirrors itself. Okay, so as an additional optimization, we've heard a lot about inodes. So typically those user or CI Spack instances live in a tempfs. So it's like 20 to 30,000 files with Spack and the configuration files. But we still don't want to transfer that over NFS or some other parallel file system. We don't want to transfer so many files, so we compress it using a squashfs, and then the copies themselves are created from this one file that is transferred over the network and then decompressed into the tempfs of the compute node. The logical extreme of this is that you have a fully set up deployment with the bootstrap mirror and the Spack mirror, and the configuration files for your environments and the Spack checkout. You compress the whole thing into a squashfs, move it over to the air gap, and then the setup on the air gap system is exactly the same as with a regular system that might have internet access. So from a developer point of view, this is what you see. You have a shared deployment instance. Those are versioned. We try to have a new one every 3 to 4 months. They themselves create a copy during each CI job, or if they want to do development on top of it, they create a user copy that may be persistent. That allows them to make local modifications. We already saw how to make the change with Spack develop to point it to our source code. Another modification typically is we have the Spack repo that will modify some dependencies, like add a new version maybe. And another trick is to have a Git redirect, where you have local Git repositories somewhere that will be used as installation source for Spack. So, okay, this is just what I've just said mostly, and yeah, any questions?
Questions? Someone surely has a question.
How hard was it to get developers to adopt this workflow?
I didn't give them a choice. That's so I'm the Spack CMake guy, and in the end, they relied on me to get them all their software stacks on El Capitan and the other systems, and I gave them this workflow, and it was field tested in our hackathons, and once they got used to it, they just didn't want to switch back.
Nice. Any other questions? Because I have one. No? Okay, can you go back to your picture of the shared file system and the environments coming out of it?
Yep.
Yeah, this thing. Can this not just be an environment with the install tree overridden? Like, does this not, can you avoid having a separate Spack checkout for users here and just make that an environment?
I could, but I want to give my developers full control. So they cannot, typically there are some things that Spack writes into its own installation, and that just, I avoid the whole issue by just having my own Spack tree.
Yeah, okay. I guess I'm curious if we got rid of that, if that could just be an environment and we could avoid. Yeah, the GPT. Yeah. Okay. We should make sure that goes into the pip to the standalone Spack.
Yeah. So I'm really interested in the pippable thing, and also the other, like you see, my includes are getting really, really long. Yes. This is not actually how I edit these environments. I have a meta language that uses templates and merges this to this final result. So I'm really interested in the recursive includes.
Yeah, and we have in recursive, we're going to have environment includes as well, so you can include an environment from someplace else. So I think that would be like 2 lines with that.
Hopefully,
so, yeah. Okay. All right, well, let's thank our speaker one more time.